So welcome everybody to my talk. It's great to be here. What I want to do is more giving an overview of several topics, so I don't want to show too many equations, and giving you some simple introductory pictures into various topics. And so the title of my talk is Quantum Gases at Very Large Scattering Lengths, so the ability to tune the scattering lengths to very large values. That's a key ingredient, and you will find it in several different topics. And so the outline of my talk, the lecture program, is shown here. The first part, I have 4 topics, and this is a general discussion on length scales in quantum gases. Then tuning via Feshbach resonances, some elementary collision processes, and a little bit about Feshbach molecules. In the second part, I want to give you my version of the Yefimov story. Dörte introduced it already, but I do it a little bit differently. And I will speak about the BEC-BCS crossover also a little bit differently. And if time permits, then there are some more topics I want to flash to you. Okay, let me start, with part 1, what we can learn from just looking at different length scales. Okay, so now question for you. Length scales, I can think about the size of the Milky Way, 10 to the 20 meters roughly. I can think about the size of the atomic nucleus. Do we care about these things? Okay, maybe there's some deeper cosmological reason why this is relevant for our field. One never knows, but I don't know. The size of the nucleus is maybe indirectly because it determines a little bit the spectral lines that we use for probing the exact position, but this is not what I mean. For the physics of the quantum gases, I think it's not relevant. The spin is relevant, but not really the size. So we care about other length scales, and we don't care about the Milky Way because it's essentially going to infinity, and we don't care about the nucleus because this length scale is essentially 0 for us. So these length scales, they exist, but they drop out of the problem. We care about, in our field of physics, the interparticle distance, which is somewhere on the order of a micrometer, maybe a little bit less. And we care about the interaction, which is on the range of nanometers, or maybe a little bit more, depend on what exactly you mean. And so now I want to point to an important difference of my talk to Dörte's talk. For Dörte, the trap length scale, the size of the trap really matters. And I look at a large system of essentially infinite size. Okay, so now the question is, what is a gas? And the answer is, the gas is a system of point-like particles, many little points, and they move freely, and sometimes in some rare events they collide and interact with each other. So that makes up a gas, and this gives us a length scale now, the typical interparticle distance. I use capital L, and this is just n to the minus 1/3, where n is the number density. So this is one length scale we care about. Then there is another length scale, and this is when the particles interact, when they get very close to each other. There's a characteristic range of the interaction, and this is, I call it R0. You can look at the size of the little billiard balls, but maybe also of the van der Waals interaction and other things. So this is the typical size. So gas is a system where this R0 is much smaller than L, and the ideal gas is the limit where R0 over L goes to 0. Very simple. Okay, but now what is a cold gas? Cold gas is a gas some of you have in the lab, and where we care about the wave nature of particles. And how do we see the wave nature? So one thing is we care about the thermal de Broglie wavelength. And this is the usual definition of the thermal de Broglie wavelength, containing here in the temperature. And this is another length scale now we have in the quantum world. And this is very important for us. And then if we look at collisional interactions, then we can ask ourselves, when do collisions become quantum? Okay, now let me look into this regime here where the thermal de Broglie wavelength is much larger than the interaction range. Long wavelengths, small particle. What happens even if you look into classical optics, Rayleigh scattering, you cannot resolve any structure. Scattering becomes isotropic, and Yeah, and for us, this is the S-wave dominated regime, where we care about S-wave interactions. So if you look into your quantum mechanics textbook, you find something about the partial wave expansion. And in our case, all the higher partial waves, P, D, F, G, and so on, they all freeze out if these parameters are not over lambda goes to 0. And what is important for us, at least if we have particles where symmetry does not forbid this, is that only S-mains are remaining, and relevant length scale is now the S-wave scattering length A. Now we have another length scale. Okay, now the question is what determines the length scales R0 and A? And Dörte gave already an introduction, into the two-body scattering physics, just the main ideas. So this shows some molecular ground state potentials, triplet and singlet potential of the lithium-2 molecule. And you have typically 100 bound states here and maybe around 30 here. And what is relevant for us is what happens at very long range. In very long range, you don't see anything in this plot, but this is the region where we have the van der Waals interaction at work, and the van der Waals interaction then follows the r to the minus 6 law. This is an r to minus 6. This is the van der Waals interaction. And from the van der Waals interaction, we get another length scale. This is the van der Waals length. Dörte has already introduced it. Maybe you have another prefactor in front of it. There are some different definitions around, but I use this one. You use the same symbol, but we have a slightly different definition. It's only a numerical factor, so we don't care here, the numerical factors. The length scale characterizing the near threshold molecular interaction is this van der Waals length I get from this expression. And this now takes the role of this short-range interaction, this what I called R0 before. Now, the van der Waals interaction gives also a typical value for the S-wave scattering length, some kind of an expectation value, but it can strongly vary because of resonance effects. It can be 0, it can be very large, but somehow, you get highest probability around these values of van der Waals. Just to give you some numbers, we like to express it in units of the Bohr radius, which is given here, roughly half an angstrom. And for the alkalis, lithium-6, we have 31.3 Bohr, and for cesium, we have a little bit more than 100. So this is just the order of magnitude. Okay, now we look again into these potentials, and the point I made already is there are many vibrational levels. But what is relevant now for the scattering length is essentially what happens very near the threshold, and what is important is where is the location of the last bound level. This is closely related to the scattering length. So last bound level, which is very, very close to threshold, means we get resonance scattering length. Resonance scattering. Okay. Now I have 4 length scales. The interparticle distance, the thermal de Broglie wavelength, the S-wave scattering length, and the van der Waals length. And now I can consider the hierarchy of these length scales, and I want to show that this determines in which physical regime you are in. Now an example, simple example. Who's working with rubidium here? Okay, so rubidium gas is a simple laser-cooled rubidium gas, let's say 20 microkelvin, and the number density 10 to the 10 per cubic centimeter. Okay, then I can calculate a length scale L now. My typical separation is here 2.2 micrometer, which is in Bohr 88,000 Bohr radii, very large. Now the next one is the thermal de Broglie wavelength, which is 800 Bohr. You see there's a factor of 100 in between that, and this means you have a classical gas. Okay, the laser-cooled gas, we know it's still a classical gas. And then I have the other length scale, and this is, in this case of rubidium, very close together, the scattering length, 100 Bohr, and the van der Waals range 83 Bohr, and these numbers are much less than that one, which means we are in the S-wave dominated regime. Okay, so we have a gas which is classical, but which has quantum effects in the sense that I'm S-wave dominated here. Okay, so that's the laser-cooled rubidium gas. Now I look into quantum degeneracy, and you know, of course, your textbook formula n times lambda cubed should be larger than 2.612. And I can also express it, I can take the third root of it and express it in terms of the ratio of the two different length scales. This should exceed 1.38. I can also set up a similar criterion for a degenerate Fermi gas, T smaller than TF, and then I get, with few lines of calculations, I get lambda over L is larger than 0.91. Okay, and this is on the order of 1. So let's say the onset of quantum degeneracy you get when the thermal de Broglie wavelength is on the order of the interparticle spacing, which nicely fits to this intuitive picture of somehow overlapping wave packets. So this is about quantum degeneracy. Then another thing, Bert has also mentioned this already, is a diluteness condition for quantum gas. You often find it in textbook as A cubed should be much smaller than 1. And this means essentially, I can again take the third root of this, A should be much smaller than L. Very simple. That's the diluteness condition expressed for the scattering length. Okay, and now I draw a long arrow here. And this long arrow is now a length scale. Let's say it's a logarithmic scale. Yeah? And then I put down my length scales. And then you see the thermal de Broglie wavelength here is larger than L. So that means it's a degenerate system. And here A and R van der Waals are much smaller. So this is a typical situation of a weakly interacting rubidium Bose-Einstein condensate, what you see here. So there's a large gap here between A and L. Here interactions can be understood in terms of simple two-body interactions, and the mean field description of the BEC now works very well. But now, how about the tunable gas? So if I have a knob to change the interaction, also tuning the scattering lengths, you know already how we can do this in the experiment. But what happens, I have a variable A, and it can be small here, then it's a dilute gas. But if I approach these numbers here, then it's no longer a dilute gas. Now I can ask what happens if I increase the scattering length. First of all, I start in the dilute quantum gas regime, then A is over here. Then with increasing scattering length, somewhere in between, actually when A becomes much larger than the van der Waals length, we get some kind of universality. That's the interesting regime where universal few-body effects like the Yefimov states happen, or can happen if it's a bosonic system. If A now gets close to L, then this picture of simple two-body interactions, sometimes they interact and otherwise they move freely, breaks down completely. And you have to think about, increasing role of many, of few and higher order few and many body interactions. And this is already now the regime that of many body physics. In a strict sense, if you say is it still a gas? Not really, because this picture of free propagation, sometimes collision, it breaks down here. It's just a quantum many-body system. And the extreme case, when I tune A to infinity, Dörte mentioned this already, that is a unitary gas, and the interaction now is fully resonant, and the scattering length gets infinity, and therefore it drops out of the problem. It's just as large as quantum mechanics allows. Now, this is now our route from few to many-body physics, connecting to the title of this nice conference. Two famous examples I want to discuss a little bit more in detail in the second part of the lecture is in the boson world. You have a situation like this. A is large, but not yet here, and its lambda is a little bit smaller than L, so it's not yet quantum degenerate, but it's very close to degeneracy. And this is the interesting regime for Yefimov states and for universal few-body states here, related to the Yefimov states. In the fermion world, it looks like this. I can completely forget about the R van der Waals. I have the L, and here I assume T equals 0, which means this lambda drops out of the problem. Then I simply have the interparticle spacing, and now I can tune A very large, can also disappear. Then I have just one parameter left. That would be the unitary gas, and variations of A here would be the BEC-BCS crossover. I will discuss in there. Hopefully, if I have time in the second part of the lecture. Okay, just one note. I like to discuss length scales. You could also alternatively, if you like this more, discuss various energy scales. And quantum mechanics always link the length scale to an energy scale by this simple expression here. Note there may be some numerical prefactors, there may be a 2 or something else. This is not exactly defined, but this gives a general picture. And then you can also discuss different physical regimes in terms of energy scales. For example, Goethe started with the composite particles, and you can say now, a composite particle, now we care about interaction effects on an energy scale which are much, much smaller than the binding energy of these composite objects, and therefore the composite nature drops out of the problem. This is an energy argument. And this breaks down then with the BEC-BCS crossover, and at the end, so the molecule that I can form, just the binding energy gets so small that this separation can no longer be made of the energy scales. Okay, 2 examples, just the thermal energy scale. I mean, I calculate from this expression with lambda, then I get the thermal energy with a factor of 1 over 2 pi. Always these numerical prefactors, yeah. And then this one, if I just take the length scale A and I calculate the energy scale, I get something very important, and I will discuss it some detail. It's the binding energy, universal binding energy of a dimer in the last bound level. Now let's continue with part 2. Tuning the scattering lengths. I want to discuss a little bit the magic of Feshbach resonances. And you all know that this is our tuning knob, and you all know plots like this, and you know these formula well describing isolated Feshbach resonance. Sometimes physics gets more complicated when they overlap, but for isolated resonance this works very well. And I have 3 parameters in the problem. One is the position, and here in this plot it's shown relative to this position, B minus B naught. B naught is the position of the resonance. I have a resonance width, which is actually from the distance of the pole of the resonance to the zero crossing. And in this picture here, the scale, the magnetic field scale, has been normalized to this delta, to this width. And then I have the scattering lengths, which are normalized to the background scattering length. So far away from resonance, it's a constant background here, which is given by this part here. So that's the Feshbach resonance, and I think you all know this. But we have to also consider, so what is below the threshold then? It's a molecular state that causes the Feshbach resonance. And the molecular state has then a variable binding energy. If you vary the magnetic field, you can vary the binding energy. And there is a certain slope. In the case I neglect the interaction, then this state has a certain slope. And this slope, relative to the threshold, this is the threshold, gives the differential magnetic moment. And this differential magnetic moment is our 4th parameter. We need not 3, we need 4 parameters to characterize the resonance. This delta mu is important. In many cases, it's just on the order of the Bohr magnetone, but there are some exceptions where this delta mu is very small, for example. Okay, this is, we need 4 parameters, and here's an interesting region, very close to the center. It's no longer a straight line. It's bent and becomes a parabola, and this is what we call the universal regime. And one thing is, in the universal regime, we get the universal binding energy, which is the expression I've shown before, which is simply h bar squared over ma squared, where this energy is directly related to the S-wave scattering length. Only in this regime, this relation here holds. And further away, it's a different story, and the state becomes essentially straight or couples to other molecular levels. But this is the universal binding energy. Okay, so now I want to give a very simple cartoon-like picture for a certain limit, which is important for our experiments, of the Feshbach physics. Here we have the scattering potential. There are many bound levels, but we only care about the last one, which is very close to threshold. And this is our entrance channel for the 2 atoms which collide. Okay, this is the entrance channel, and now the Feshbach resonance arises because we couple to another molecular potential. We call it the closed channel here, and this has a bound state. It has many bound states, but one of the bound states is very close again to the threshold and to the other state. Okay, and the Feshbach resonance comes from coupling of these states, and the tunability comes from the fact that normally these states have different magnetic moments, they tune differently, and you can shift them then in resonance by tuning the magnetic field. Okay, but now what is the simple picture? Now the simple picture is, now you get a coupling between those levels, what we call the Feshbach coupling, and this shifts a little bit the states. Look here are the states, look at the upper one, and now I shift them a little bit, so it's it's lowest order here, the coupling, it's not strong, it just means that we have a certain shift. And then it can shift the upper state exactly in resonance, exactly on threshold. And then I have a situation where I don't really have to care about the population in this state, but the lowest order effect is simply this shift, and that causes this scattering channel, the entrance channel, to be fully resonant. And then I get this simple picture, again I recover the simple picture of scattering in one potential only, I have my last bound level on resonance or very close to resonance. I don't have to care about the other channel. And this is a simple picture for what we call an entrance channel dominated, or in a little bit more sloppy but shorter words, a broad resonance that's the picture. But then we ask, what is a criterion? How can we say the resonance, what is the character of the resonance? When does this simple picture apply at all? Okay, now I come back to my favorite length scales, and I can write down another length scale, which we sometimes call the range parameter, or the R star, or sometimes the Petrov parameter, because it first appeared in this paper. And these, the resonance parameters that I have, I mean delta mu, background scattering length, they define now a new length scale, R star. And if this R star is much smaller than R van der Waals, then I have an entrance channel dominated resonance, then I don't care about this length scale, which is so small I don't care about it. It's even much smaller than R van der Waals. I don't care about R van der Waals if I'm the universal regime, let's say, of Yefimov physics, and then I don't care about this one. But this is only working for these type of resonances. And in this limit that R star over R van der Waals goes to 0, we don't have to care about this additional length scale. So this picture is simple. We just need A, and we need these R van der Waals perhaps, and then that's it. Okay. This leads to universality, and in this regime, on the Feshbach resonance, also this universal dimer binding energy holds. This only holds if I can forget about this R star. Then this simple equation I show several times holds. Now the opposite case is a closed channel dominated resonance. It's a long word, but we sometimes call it a narrow resonance, which is shorter. And here R star is large. And then it really becomes a relevant length scale. And we are confronted then with the situation that we have another relevant parameter. So in general, the theory has to take into account our description, this R star. And you can still say it's a kind of universality, but not only with a single parameter, so you need two parameters, a two-parameter universality. Okay, and then there are some intermediate cases, and there are some cases where A is so large that it even far exceeds R star. And then I can again forget about this R star, and I get full one-parameter universality recovered at very large scattering length. Now, these are some simple arguments on that. Now, again, my logarithmic length scale and the universal tuning range, and now see I have, in addition, I have these R star, R van der Waals, R star, A, lambda, L, and that means if I have a broad resonance, then this R star goes to the left and disappears, and this gives then if on broad resonance, I get the widest possible tuning range for universal physics. This is where universal physics can happen. And then the theory based on a single channel picture works. On narrow or intermediate resonance, the physics is different. I need an additional parameter, and the theory has to be based really on a two-channel description. Okay, so this is an overview of selected resonances. That is from our review article we wrote a couple of years ago on Feshbach resonances. There you find all the details in this review article. And there are also, we put this plot here, which shows here a dimensionless parameter called the resonance strength. And this is just R van der Waals over R star with some factor which is very close to to 1. That means strong or broad resonances have a very large S-res parameter, and here are the narrow ones. And this is now the width in terms of the delta, and this is the resonance strength. You see a general trend, of course, here, but I mean, it's different, and the difference is made by the background scattering length and also a little bit by the differential magnetic moment. Okay, and now I just want to introduce two extreme resonances. So this is the resonance here for the fermions that is often used in BEC, BCS crossover physics. It's a quite strong one, S-res more than 100, but it's not the most extreme one. The most extreme one that I know you find in cesium. At near 800 Gauss there is a super strong resonance where S-res is, I don't know, extremely large, more than 10,000 or so. And this is kind of a world record holder in strengthness of a resonance, the most entrance channel and dominated resonance that exists. And I just emphasize this because we have used these resonance for some of our experiments on chemophysics. Okay, so I will talk about these resonances in my later lecture. In my talk on Thursday, I will talk about another resonance in a Fermi-Fermi mixture, which is kind of narrow, not extremely narrow. There's still some universal aspects in it and a universal regime, but you can call it also an intermediate resonance in a many-body sense. But that's for the talk on Friday. For today, I stay with the entrance channel dominated resonances here. Now, a few words about elementary collisional interactions here. Just want to make a few points. And just want to show the first observation of a Feshbach resonance in an ultra-cold condensed sample. That was sodium BEC work at MIT, now almost 19 years ago. And they observed for the first time the effect of a Feshbach resonance on Bose-Einstein condensate. And you see two things, the upper panel and the lower panel. And the upper panel shows that when you approach a Feshbach resonance, one thing you encounter enormously fast losses, which seems to be bad, but we see that it also has very, very interesting sides. Then, for BEC tuning, what you want to get is this dispersive shape. So this is the elastic part, looking at the BEC expansion, where you can monitor somehow the changed scattering length, and this shows the behavior that was described by the expression I showed before. That's the elastic part, the inelastic part. So in the first, years of BEC research, of course, this was interesting, the elastic part. I mainly wanted to tune the scattering lengths. And just two quick examples. This is tuning the elastic interaction in a rubidium-85 BEC by the Wyman-Cornell group. And this just shows when I increase the scattering lengths, actually they reached pretty large values of about 6,000 A0 at the end. This very small scattering length, they increase it, and then they simply see how the equilibrium size of the BEC is growing. But you can also tune the scattering length to very small values, much smaller than these van der Waals, very close to zero. And if you tune it to slightly negative attraction, then something interesting happens. Then you can form solitonic wave packets in the BEC. So this is kind of an elongated kind of waveguide for a BEC, and then you see the BEC splits into little solitonic parts. This is also early work by the Hewlett group in 2002 published. But this shows the effect on the elastic interaction. Okay, now let me look into losses. First of all, losses can be very nasty in experiments. One thing is, if you have two particles collide and one of them has, or at least one of them has some internal energy, principally you can release this internal energy. And then if you release it, then you find the internal energy. Part of it is in one collision partner, the other one here. If they have equal mass, it's just 50-50. And this energy scale, normally, this is, even if it's a magnetic energy in the Zeeman substructure, this energy can be very large on the scale of our experiments and leads to immediate trap loss. Okay, so here's one example, and this is an example of these two-body loss measured in a lithium-potassium mixture near the 155 Gauss Feshbach resonance. And we see that these rate coefficients for loss are really large. And what happens? Actually, it needs some change in the total magnetic quantum number. If I look into the two atoms, and it's normally suppressed. But close to a Feshbach resonance, the probability that they get very close together is resonantly enhanced. So the wave function is enhanced. And there you have dipolar coupling, and this dipolar coupling leads to this fast decay. So two-body loss on a Feshbach resonance is sort of almost unavoidable and can be very, very annoying for the experiments. What can I do against these losses? In many cases, very simple solution. Put the atoms in the ground state so that they don't have any internal energy. And then there's no energy release possible, very easy, and you have no two-body loss. And you're happy if you have your Feshbach resonance in this lowest spin channel and you don't suffer from two-body loss. It's not always the case, but in many situations. Therefore, it's a good reason why most of the current experiments in strongly interacting gases are carried out in systems where you are in the lowest spin channel. You don't have internal energy. Cesium example, just bosons in the F equals 3, MF equals plus 3 state. It's the lowest internal state. You don't have any two-body loss. So the next order loss then, if three particles come together, is three-body loss. In three-body loss, you form a dimer. This releases binding energy. And this binding energy has no other option as to go to the kinetic motion. So you find it as kinetic energy of the dimer and the atom. And also this energy can be, in many cases, very large and lead to immediate loss. Sometimes it's very small, and then it leads to heating, but in many cases it leads to immediate loss. So this is now three-body loss. And for three-body loss, if I consider the most simple situation of three bosons, then one can show, even with simple dimensional analysis arguments, that in the regime of large scattering lengths, where this is the only one relevant length scale, the loss coefficient in this loss equation, so n dot is minus L3 times n to the third, this loss coefficient scales proportional to 8 to the 4. And then you have h power m there, and then there's a prefactor containing a number c. So for the moment, I mean, just look at this one. There's the 8 to the 4 scaling, so it's really a dramatic dependence. Change your scattering length by a factor of 2 only, then you get a factor of 16 change in your loss, and that's already quite substantial. And if you want to change it by one order of magnitude, you get a factor of 10,000 here. Yeah. So it's a dramatic dependence. And for a little bit later, then, this C is not only a number, it contains some more very interesting information. Actually, it's another function of A, but that's what I want to discuss later. So for fermions, the situation is different because of Pauli blocking effects. In many situations, like the systems potassium-40 and lithium-6 used for the crossover work, we have a situation where we have one of the fermion in the lowest state, the other one in the second lowest state. Then they become non-identical and can collide in S waves. And this situation turns out to be very stable, even extremely stable for lithium, even if you are in the Feshbach resonance. That's one benefit. And if you look into the three-body world, I don't want to discuss this really in detail. Dörte discussed this a little bit. I mean, three-body recombination with two particles spin up, one spin up. Okay, or three identical particles. Depends on how many identical particles you have involved. And then also three-body recombination becomes, first of all, energy dependent, because you have to rely on higher partial wave processes. You get an energy dependence. That's not the case for the three boson system. The collisional energy in the threshold regime, it's independent of the collisional energy in the threshold regime, and it has more complicated scaling as a function of the scattering length. Okay, but now my part 4, short part, okay, is now on two-body bound states. Just a few words on Feshbach molecules. And you have seen this plot already, this graph here, and we are interested in that region here, where we get a molecule. And one way that we very often do in the experiment is a Feshbach ramp. So we start with atoms here, and we ramp in that direction, starting on this side where you have negative scattering lengths, I start and ramp down in an adiabatical way the magnetic field, and then I enter the molecular state and can create a dimer here. This is commonly used in many experiments. This doesn't work in the perfect way, at least in a free system. In a lattice, it works in the perfect way, but in a free gas, because you have to fight against losses and these things, but you can conserve decent fraction. Another thing is using radio frequency to put them together, and in some situations you can use three-body recombination. So then these molecules that I introduced before, created by three-body collision events, are in this state, and then you can use them for further experiments. That's also relevant for lithium-6 in the crossover regime. Okay, that's how you form them. Then here are some two early examples. A couple of years ago, 2003, then it really started with these Feshbach molecules, and I think two very early experiments by David Jin's group on potassium-40, by our group in Innsbruck on cesium condensate. And so the idea is just to put two atoms together and form a dimer, and then there are some tricks how to detect them. And in our case, it was just, if you form the dimers, they have a different magnetic moment. And if you have a magnetic gradient, you have a Stern-Gerlach effect, which simply separates the molecules immediately from the atoms. And then you break them again by dissociating them, you detect the atoms. Here it's a little bit different, the scheme, but it's also a scheme that relies on dissociation, Stern-Gerlach effect, and then imaging of the molecules. So this was the first positive signal of seeing somehow these molecules in experiments. Okay, but now how do we use Feshbach molecules for various purposes? And one important application is the creation of ground state molecules. Now several groups are making good progress on producing ground state molecules with a large dipole moment. And the starting point then is in a gas are usually Feshbach molecules. You first associate Feshbach molecules here, and then using a two-photon transition, don't want to go in any details of these states here, two-photon transition, you go down to the ground state of the molecule. So that's one important application of the Feshbach molecules. But you can use them also in a general way for detecting pair formation and many applications. Okay, but now let me come back to this picture and to this universal regime. I want to make one point. I've shown this several times. It's so interesting, I showed it several times. And it's a very interesting situation for few-body physics, because I want to look at the character of the wave function. And it looks like this. So here I have the potential. Somewhere here is our van der Waals. And now I have the dimers in a very weakly bound state. And that means here, outside, it's a classically forbidden region, but the energy difference is very small, so it tunnels very far in the outer region to very large R, so therefore I have an exponential decay of the wave function. So it's really funny. So I mean, the interaction is like this. The molecule has a size like this, yeah, and the dominant part of the wave function is there outside. So the probability that they get close together, it's very small. Yeah, but they are mostly in this forbidden region. And this is a so-called quantum halo state. Halo states, such states are known. They are known in, for example, in nuclear physics. Some of the nuclei show this halo character. They are known from the helium dimer. The helium dimer has also halo character. But these are really extreme examples, follows this universal binding energy formula very well. And that's what I pointed out already. You find it in the deuteron, the helium dimer, and several nuclei. But this is really an absolutely extreme regime. So we can reach conditions where this A, so the extension is more than 100 times larger than the van der Waals range. Yeah, that's really extreme realization of these halo states. And these halo states then will become important for the few-body physics parts. And I think this is a good point now to stop the first part of the lecture. And if you have some immediate questions, I'm happy to answer them. And otherwise, we have the long discussion session in the evening.